All right, so let's just take a moment to breathe. I'm sure some people will come in, but that's okay. All right, feet on the ground, pens, pencils down. If your phone is peering at you, maybe turn it over. If you feel comfortable, close your eyes. Otherwise, just look somewhere peaceful. If this kind of thing is not your jam, that's fine. Just be still for a little bit. And start listening to the sounds around. Gradually bringing your attention closer and closer to yourself. And now transfer your attention to your breath. Notice the breath as it comes in through your nose. Notice how it's cool at the back of your throat. Notice how your chest and your belly expand as you breathe in. Notice that there's a still, quiet moment between breathing in and out. And then as you breathe out, shoulders relax, belly relaxes. So for 3 whole breaths, just notice how you breathe. If you find your mind has wandered off, that's okay. Notice where it went. And just bring it back to the breath. 2 more breaths. One more breath. Just breathe. And start listening to the sounds around. Wiggle your toes. Give a nice stretch, even if you need to, and open your eyes. All right, so what we were just doing was line integrals of surfaces. So what we were doing was we were taking some scalar function, which looks like, for example, x squared plus y squared. So remember, that is a scalar function. You put in an x and a y and you get out a single number. And we were integrating a scalar function over a particular curve that we were interested in. Okay, so that's what we were just doing. It just sounds fancy, but yeah, that's what we were doing. But we've already just learnt about these things called vector fields. So the question might be, well, I've got a vector field, so this is also something that lives in 3D. Maybe I could integrate that along curves. Wouldn't that be fun? Okay. Maybe not that much fun, but why would we need to do it? Okay, because if we're doing physics, it turns out, sorry, this is all about physics, you're going to need to do it. So let's just think about it. So if you're not a physics person, you can space out now. For physics people, I'm just giving you a justification for why I'm going to put you through yet more integration. Okay, so you know about finding work. Work is force times distance, but really it's the force dot producted with the distance if the force is constant. Yes? Yes? Yes. Okay. So for example, you ask questions like, what's the work done by gravity to move a 10 kilogram box 5 meters down a frictionless ramp that's at 45 degrees? And you would work it out using that F dot D. Lovely. Okay. But there's a small problem. What happens if F changes? So notionally, when we're working with gravity on the surface of the Earth, we don't worry about it not being, we treat it as constant. But technically, gravity changes depending on how high you are above the Earth and stuff. And there are many other situations where a force that's being exerted changes depending on where you are. And then you can't really use that dot product formula because depending on where you are, the force is different. So F dot D is not going to work. So what do you do? Well, to put it into the language that we've been using, suppose we want to think about the work done by a force that varies with position, moving an object along a curve C. Okay, so we're going to move our object along here, and at various different points, the force is different. Well, then what we really want to do is we want to say, okay, let's do what we always do. Let's zoom in And then we're going to say, okay, let's just consider this tiny little bit, which is where the force is almost constant and this is almost flat. And then along here, along this tiny bit, we can kind of use F dot D. But it's really the tangential component of our force, because if F dot D, we want the tangential component of our force times that distance. And then we do it for the next little one, where our force has changed again, so we'd find a new thing and add them all up. And this is beginning to sound a lot like finding an integral. So to think about what is the little bit of work done over here, we could call that dW. It's our force at that point times the tangent vector. So this is just finding F dot D times the little distance that we've got. So here I'm using the tangent vector to get the component of F in the direction that I'm moving. Okay? And then what I need to do is I need to sum all those up. So I need the integral of dW, but really what I'm doing is an integral along the curve of all these little bits that I'm finding. And suddenly we are integrating vector fields. That's what we're doing. Okay, so what is our little tangent? We know that our tangent is always dr by ds. We work this out. So TDS is, sorry, dr. So finally, we can put this all together and say that our work done is the integral of the dot product of our vector field with our little dr. Okay, as I say, this was a physics interlude to kind of motivate why we would want to be able to do these sorts of integrals. And, well, this is why. So essentially, if we're wanting to find the work done for a force that is changing in position, we're going to need to do this. Okay, so we can take what I've just said, and more generally, now we're not thinking about work, we're just saying, okay, find this integral. If we want to find the integral of a vector field along a curve, then the line integral of the tangential component is given by this. Okay, if it's feeling like what the hell, just remember what you're doing is you're finding the work done by that force along that curve. Okay? And remember all the things that we've done so far. So we know about how to deal with dr. We'll see it again, but we know how to deal with it. We know how to deal with f, that's a vector. We know how to do dot products. We have all the components here. Okay, so...
sorry.
Yeah.
Here is the F1 the partial derivative, or is it
Nope.
the... Okay. Yeah.
Okay, so this is why I don't ever think one should use subscript 1 as a partial derivative, because mostly it gets used to talk about, so F1 here, again, this is the x component, not partial. Okay. Let's just look at some examples, which is the best way to learn. Yeah.
I'm a little bit confused about why we're using the tangential component of the force. I mean, this may be a dumb question.
No, it's not a dumb question. We're using it because, well, what we want to find. So the motivation for it was thinking about finding work done. And work you find from the dot product. So essentially, the dot product is giving you the component of the force in the direction. So the dot product gives you the tangential component of the force in the direction you're going in. Now we're kind of abstracting that. So we're saying that what we want is the line integral of the tangential component. So that's what we're just stating that that's what we want, because it makes sense motivated by the fact that usually we're trying to calculate work or something like that. Yeah. There could be situations where instead you actually wanted to use the radial component or something. And in fact, we'll see that later on. But for the moment, we're doing the tangential component. Okay, so here's our force. So it's got an x component of y squared and a y component of 2xy. And you want to evaluate the line integral from 0 to 1, 1 And we're going to do 3 different paths, which sounds crazy, but there's a reason for it. Okay, so let's set this up. So we know that what we need is we want to end up with okay, so I'm just putting this over here just so that we've got it. Okay, so the thing that we're trying to work out is this over here. So we don't want to have to integrate vectors because we don't know how to do that. We want to do single variable integration because that is solid. And in order to get to single variable integration, we are pretty much always going to do what we just did previously. We're going to parameterize. So I think you would all feel a lot better about that integral if it was just a straight single integral with respect to t, right? So let's make it so. So we're told that we want, so the first one that we're having a look at is we want to do this integral on the straight line y is equal to x. So let's just draw a little picture of what we're doing. Okay, we're going from 0, 0, which is over here, to 1, 1. And for a, we're going along a straight line. So we want that line there. So parameterize however you feel. I'm going to go with the simplest possible one. Well, any suggestions?
X equals t, y equals t.
Let's just keep it super simple, and t goes from 0 to 1. Okay? So this tells me that my limits of integration will be 0 to 1. Okay, so then I know that my r of t is going to be equal to tt. So I'm using slightly different notation here, but you can use, actually maybe I shouldn't, let me stick with the old notation that I've been using. Okay, and I'm going to need dr by dt which is just okay, we'll see why I need that in a moment. And I just want to get my f, which is equal to okay, so I want to transform my f. I also want it to be in terms of my parameter t. I've got a y squared, so that's going to be a t squared. And a 2xy, so that's a 2t squared in the j hat. Okay. So I've transformed all my components, and now I need to transform this crazy cat thing over here, f.dr, into something that just involves t's. So I need to get my t in there. And this is where I do the good old trick of saying, okay, I'm going to write dr as dr by dt times dt, lacerating the field of any mathematicians by just saying you can multiply top and bottom by dt, whatever the hell that matters. Okay, but we've done this before. So I can rewrite this as the integral of f dot dr by dt all multiplied by dt. And now I've got an integral with respect to t, so I've got from 0 to 1. So I've gone from this thing over here, which I'm not very clear on exactly what that is, to this is a dot product I can do, because I have my vector dr by dt, and I have my vector f. I can take that dot product. It's going to give me a scalar, yay, okay, and that scalar just depends on t's, and I'm just going to integrate with respect to dt and move on with my life. Yay, okay. So if you do that dot product, so we have f dot dr by dt, you can just multiply it out for yourself, but you'll get that it's 3t squared. So finally I have my integral and if you follow that through you'll get 1. Nice. Okay. All good? Let's do it again. Okay, so the next one we're going to do is the same integral, but we're going along a different curve. So our start and end points are the same, but now we're going along the curve y is equal to x squared. Okay, so now we're going so start point is the same, end point is the same, but the curve that I'm going along looks like that. Yep. Let's parameterize. Okay, so I want some parameter t, and as I vary x, it's going to move x and y. As I change t, x and y will move along that curve. What should my parameterization be?
X equal dy by x squared, that's the radius one.
Seems reasonable. And my limits? So as we've said before, this is just a simple parameterization. You do you, okay? So long as it's a parameterization that works, it's all good. So we can follow through doing exactly the same things. So now our r of t looks like this. So our dr by dt looks like that. So now it turns out that our dr by dt is time dependent, but it wasn't before, but that's okay. And our f has also changed its form. If we write f as a function of t, we've got t to the 4. Because all I've done is I've plugged these, so I have a y squared, which is t to the 4, and a 2xy, which is gives me a 2t cubed. Okay? And if we plug this all together, I'm going to skip some calculations here. When we take our dot product that we're interested, it gives us 5t to the 4. And so finally, if you do your integral the way we just did, I'm going to leave some details for you to fill in, but what you will find is that you get 1, which we just got before. Okay. And in fact, if you do part C, you will get 1 as well. So we go along a different route here. It says the straight line segments from 0, 0 to 0, 1. So this one says go along the path from here to here, and then from there to there. So quite a different path from the ones we've been doing, but still starting same point, ending in the same point. If you do that, and please do it for homework, so you can split this into 2 integrals. So first do the integral along that path, and then add it to the integral along that path. You will get 1. Which seems suspicious, right? I mean, why? And this leads us to I'm going to come back to that in a moment. This crazy thing, this link between a conservative vector field and a couple of points which say that if you're a conservative vector field, then if you have any 2 points and you do this line integral, your line integral will have the same value regardless of the curve that you move along. So it doesn't care about which path. All it cares about is where you start and end. So this is another really useful thing about conservative vector fields, because what this is saying over here is someone could give you some crazy, really horrible path to integrate along. But if your vector field is conservative, you can ignore that path, find a super simple path that is easy to parameterize, work that out, and you're done. So this, for me, is like why conservative vector fields are amazing. So one thing you should go home and check is that this bunny is conservative. And that is the reason why no matter which path we pick, we always get the same value for the integral that we find. Okay. A few little bits of terminology. So if we want to go around a closed path, so the start and end points are the same, then we have a little bit of notation. So this circle here says this is a closed path. So the curve C is a closed path, and sometimes you'll hear it called the circulation of F around the curve. And you can just have a look at this. This is just basically summarizing what we've done so far. So before we head on and just finish what we're talking about, a few more bits of terminology. So when we're thinking about domains, it's often useful to be able to think about, are they split up into entirely separate non-intersecting regions, for example, like this, or are they connected? And mathematically we define these as saying it's connected if any pair of points in the domain can be joined by a smooth curve. So if I take any 2 points in there, or in fact in there, I can draw a line that stays in the domain that gets from point A to point B. So even if I go from here to here, I can do that. I mean, I could also do something like that, but you get the point. But the problem is that if I picked a point here and here, there's no way that I could join them without leaving the domain. So that's the idea of connected versus not connected. And more than that, we have the idea of simply connected, which says that if I have any 2 points and a curve connecting them, simply connected is if I have a closed curve, I can always shrink it down to nothing. So in here, there's a curve. You can imagine that I can shrink it down, staying in my domain, and eventually I can get it right down to a point. But if I have a look at this one over here, this curve, I could shrink it and shrink it and shrink it, but then the hole gets kind of stuck and it can't shrink it anymore. Okay, simply connected, not simply connected. This is going to be relevant for what we're about to say, which is what I briefly showed you, is if you're an open connected domain, and you've got a smooth vector field, then the following 3 statements are equivalent. And which means that if you know one, you know that the rest are true. And I mean, you could do the mathematical proofs to show that each implies the other. So F is conservative in D. So that tells us that we could think of our scalar vector field as our vector field as being the potential, being the gradient of a scalar field, is the same as saying that for every closed curve, for every single closed curve in D, if I do this dot product, I get 0. Okay, which we haven't really looked at yet, but that's one of the things. And then the thing that we've just seen over here, that if I'm trying to find this integral over here, it doesn't matter which path I take, it just matters my endpoints. So often, what is useful to do is someone will say, please calculate this line integral. And you'll look at it and be like, I really think that looks hideous. Let me check if the thing that I'm integrating is conservative. Once you've checked that and you find it is conservative, then you just change the path to something that's more straightforward. Or better yet, someone says, calculate this closed path integral, You're like, that looks hideous. I don't want to do that. Check if your vector field is conservative. If it is, no calculation required because it's just equal to 0. So in terms of kind of labor saving, if you have a conservative vector field, life is a lot better. Yes.
In the previous example we did, the third one was a line that was going from 0, 0 to 0, 1 and then 0, 1 to 1, 1, if I'm not mistaken.
Yep.
And is that a smooth curve as well?
Yep, it's piecewise smooth.
Okay.
Yeah.
Sorry, Glenn.
Yeah.
These three conditions that we saw, they hold for simply connected or also for connected?
So this is for connected.
But we have, like the previous slide, a hole in the middle. Then how can we ensure that the new path that we choose doesn't hold stays in the domain?
Well, the thing is you need to pick your path in the domain. So that would be on you. You need to not leave the domain. Yeah. Okay. Yeah.
Sorry, what would be a non-smooth curve then?
Anything broken?
Okay. And otherwise they're just like piecewise smooth.
So this is basically covering our mathematical butts. Mostly anything you deal with counts as smooth.
Okay.
But there are some hairy things out there that are not. But don't worry about that. Okay. The main thing to think about is continuous, like not broken.
Okay.
Yeah. All right. So just to give you an idea of... So this just summarizes what I've said. If you're conservative, then integral around a closed path is always 0. Okay? And if it's not a closed path, you can pick the path so long as you get the start and end points the same. And we'll look at this, but essentially what this boils down to is saying that if you can find your scalar field from which your vector field comes from, this integral over here boils down to literally calculating the value of your scalar field at the second point and subtracting it from the start point, which is a lot simpler than doing any integration. Okay.
Physics does make a lot of sense. The last
Right, and that should suddenly be like, boom,
Yes.
okay, a whole bunch of physics should suddenly,
Yeah.
awesome. All right, so what I would like you to do for homework is to look through this example over here. Where are we headed after this? Oh, integrals. So we'll have a look at this next week. So now we're not just thinking about finding the integral along a curve, we're thinking about integrals over surfaces. Okay, so we were finding integrals over flat domains, but now we don't want to find them over flat domains, we want to find an integral of some other function over a curvy surface. So that's where we're headed after that. And that will take us a little bit of time next week. So please revise surface elements. And finally, we will do integrating vector fields over surfaces. And then we're almost done. All right, see you next week.